Right, yeah, so our first speaker is Jon Carlson from Retired Therapy, and he was going to tell us something of the latest on endotrivial modules. So thanks again, everyone, for being here.
Is this thing working? Can you hear me? Okay. So I'm going to talk about endotrivial modules. I guess I should do the obligatory thanking the speakers, thanking the organizers for inviting me to this, but to speak. But so anyway, I'm going to talk about endotrivial modules, finite groups, Lie type. This is a project that I'm working on with Jesper Grodal, Nadia, Mazza, and Dan. I thought it was appropriate to talk about a project with Dan. He and I have written a bunch of papers together over the years. He's been just a fantastic colleague, and I've enjoyed having him here very, very much. As Bill said, I was really very insistent that we hire him when this came up, and I was. He's really been a great colleague over the years. So anyway, this is an ongoing project. It's still a work in progress in some ways. That is, we've got some things to finish up. When I say it's ongoing, I mean it's been going on and on and on and on and on. We've been working on this for quite a while, but we're still meeting by Zoom every week or two, and we're making incremental progress. And I hope we'll actually have a manuscript before too long. But anyway, here are the ground rules. We're talking about G, a finite group. It could be a group scheme, but actually for this, it's a finite group. We want a field of characteristic P. The coefficient field is usually good. We just assume it's algebraically closed. It makes things easier. It's P, by the way, is going to become L a little bit later, because P is going to be the defining characteristic of an algebraic group or finite group of Lie type. Okay, the group operator KG, the Homk algebra, you can read that. We have a tensor product operation given by the usual diagonal co-algebra structure. We can make Homk if I've got two modules M and N. I can make Homk over the K endomorphism ring, K homomorphism into a KG module by usually doing the usual thing. You've got an action on M, you've got an action on M, and basically you're doing a conjugation. And so you've got the K endomorphism ring. I don't know if you hold this. Can you see the mouse? Okay. The K endomorphism ring then is a module, and it's isomorphic to the dual of M. M star is the dual of M, the K dual of M, tensor with M itself as KG modules. So here's the definition. KG module is endotrivial if this K endomorphism ring is actually a trivial module, at least in the stable category, where you throw out projective modules. So in the stable category, you get rid of projective modules. So what you want to say is that this Homk KMM, or the K endomorphism ring of M, is just the trivial module plus the projective of some sort. So these form a group. That is to say, you can take the equivalence classes in the stable category, where again, projective modules are 0 in the stable category of these things. And what this says is, if you tensor M with its dual, then it's an endotrivial module. Then what you get is a trivial module, which is an identity as a multiplicative identity in the stable category. So we get a group out of this out of these endotrivial modules, and it's a nice abelian group because you can switch the tensor product. So it's a nice abelian group. It's been proved that it's finitely generated. That actually comes out of classification theorems, but there's also an independent proof by Pooch. And so as I say, you've got this nice abelian group. Now let me just give you some notation first, and then I'll show you some examples. The point is, if M is a kg module, then what I want, omega is going to be a shift operator, and omega of M is the kernel of a projective cover onto M. And you can iterate this. You can take the kernel of the projective cover onto the kernel of the projective cover, and you get omega squared, etc. And you can go the other way. You can take the co-kernel of an injective hull, and you get what we call omega inverse. And the point is that Kg is a self-injective ring. So injective modules are projective and vice versa. And so you can go back and forth. If you take omega of, if you've got an indecomposable module M, and you take omega inverse of omega, then what you get is M back. That's the notation. And here's the first set of examples. If you take the trivial module and you take any omega out of the trivial module, these are endotrivial modules. Okay. And same thing, you take any one-dimensional module, any module of dimension 1, and any of its syzygies, any of these translates under this omega operator, then this is an endotrivial module. And the reason for this is this sort of calculus that you can prove pretty easily. That is, if I take omega of M, tensor omega n of n, then it's omega, you just add the exponents, basically. And at the same time, if you take the dual, then you take the negative of the exponent. Okay. So these are the fact that these are endotrivial modules is consequence of actually these conditions or these properties of the omega operator. All right. Okay. Now here's some history. Here we go. For P groups, these were first defined by Dane. Actually, John Alford had a similar definition where he called them invertible modules. But this was 78 was when the paper came out, and Dane classified them in the case that G is an abelian P group. And the classification said in that case that the trivial module and its syzygies are basically everything. They're all the endotrivial modules. So the group was just well, if the P rank of the group is 2 or greater, the group is just a copy of the integers. Okay. Dane had a reason for doing this. He showed that if you've got a P-nilpotent group, then when you take the vertices and the sources of the irreducible modules, this in the sense of Sandy Green's theory of vertices and sources, that these are sources of sources of the irreducible modules are endopermutation modules, and these are built from the endotrivial modules. It was extended P-solvable group by Pooch, and Pooch also showed some other places where these come up in the block theory. Complete classification of endotrivial modules for P groups took basically 25 years to do. I mean, I was thinking about it off and on for the entire 25 years, I can tell you. And we finally with Jacques Tabenon's help, we figured this out in about 2004, 2005. Okay. Given this, Pooch was able to classify endopermutation modules for P groups. Progress on classifications for other groups, and I just give a list of names here. This is people that I could think of off the top of my head. I'm sure that I'm leaving somebody out here somewhere, but there are various people who have looked at this. in various combinations. And the motivation for a lot of this is that these endotrivial modules are basically the Picard group of the stable category. So we're interested in the Picard group of the stable category, and these are self-equivalences of the stable category of Morita type. That is, when you tensor with an endotrivial module, it gives a self-equivalence of the stable category. Okay. Okay, so I said it with an abelian group, a finitely generated abelian group anyway. So what that means is, well, you've got a torsion part and you've got a torsion-free part. And what you're interested in with the torsion-free part is the rank, that is the number of copies of the integers in there. And Jon Alpern first got this in the case that G was a P group. He said, what you do is you take the number of conjugacy classes of maximal elementary abelian groups of rank 2, meaning, so an elementary abelian group of rank 2 is a Z mod P cross a Z mod P. Okay, that's what we mean. Rank 2 means I've got 2 copies. And the torsion-free rank is this number. If G has P rank 2, if G has P rank 3, then it's N plus 1. It's 1 plus that. So it's 1 more if the P rank is 3. And so with this, basically, if you want to figure out what the torsion-free rank of the endotrivial modules are, this is what you've got to look at. You just have to figure out how many conjugacy classes you've got of elementary abelian P groups. Dan and Nadia, Mazza, and I extended Alpern's theorem using different methods to all groups, whereas Alpern only proved it in the case of P groups. Okay, so using this as one part of this project with Jesper Grodal and Nadia, Mazza, and Dan and I, we actually figured out for groups of Lie type, what the torsion-free rank of the group of endotrivial modules was. And you'll notice this theorem seems to sort of run off the bottom of the page. You're not actually supposed to read this theorem. The whole point of the theorem is that we can do it. You know, if you really want to read it, it's published. It's in the Pacific Journal that came out a couple of years ago. And so we were able to do this. And in this, by the way, we actually took a fairly broad view of what a group of Lie type is, finite group of Lie type is. I will come back to this question in a few minutes, you know, as to what a finite group of Lie type is. Okay, so that's the torsion-free part. Now, how about the torsion part? Well, mostly in the classification of P groups, basically what we showed was that there is no torsion there unless the group is cyclic or quaternion or semidihedral. And so in most cases, when you're dealing with this, when you restrict to the Sylow subgroup, if the Sylow subgroup isn't that type where it's cyclic or quaternion or semidihedral, then the only endotrivial module that you're really interested in is the trivial module. If you're looking at the torsion part, and so that's basically the story. A KG module is endotrivial if its restriction to a Sylow P subgroup is endotrivial. That's a theorem. And so if we're looking for the torsion part, what you would want is you would want the restriction to the Sylow subgroup to be a torsion module, which in most cases, as I say, means actually the trivial module. But here's the problem. So the question then really is, what we want to do is you want to compute the kernel of this restriction map from the group of endotrivial modules of G to the group of endotrivial modules for the Sylow subgroup. And we call these modules Sylow trivial modules. Actually, they've been called various different things, some of the names did not involve any profanity. you know. But anyway, this is what you want to get. You want to get this thing. And the story is any Sylow-trivial module, any module whose restricted, endotrivial module whose restriction to the Sylow subgroup is a trivial module, has the property that it has to be the direct sum n of the trivial module on the Sylow subgroup induced up to G. Or if you like, the module of cosets, left cosets of S. The permutation module of left cosets of S. So this is what you've got to have in a case like this. So this means that there aren't many of them. Okay. Because, well, there aren't that many direct subends with this module. Okay. Now, Paul Balmer actually figured out a way of doing this, of giving this. That is, he translated this into a question about what is the structure actually of the group itself. And so what we're doing is we're computing this module, these Sylow-trivial, endotrivial modules, the kernel of this restriction map. Okay? And here's what he came up with. Well, here's the basic idea of it. Got a module M. Suppose you take an element G, like, so you take an element G, and what you want is P to divide this order. So of the intersection of the Sylow subgroup with its translate. So then we can form a diagram in the stable category. That is conjugation by G takes, well, it's going to take M to itself, but the restrictions are going to be different. So you've got a restriction on K onto this subgroup, which is S intersected with this conjugate. And you can also conjugate by G and then also do this restriction. And what you're going to have to get here, if you just fill in the bottom, I mean, you know, sort of go around the curve, fill in the bottom, is you're going to have to get a linear transformation from K to itself. So a linear transformation of K to itself is what? All you're doing is just multiplying by a scalar. Okay? So out of this, for this element G, I can define a scalar coming from this endotrivial module M. Sylow-trivial endotrivial module. And this assignment then is something like you don't go from G to this scalar. It's sort of like a linear character for the group. Now, what you have to do is you have to say that G goes from 1 if P fails to divide the order of the group. And Paul called this a weak S homomorphism. Actually, he defined something more general that he called a weak H homomorphism, where H is something else. But here are the rules for this. If I've got an element of S, if I've got a function from G to the non-zero elements of K, it's a weak S homomorphism if it satisfies the three conditions given. It has to basically be the identity on any element of S. It has to be the identity on any element G if S intersected with G, with the conjugate of S by G, is prime to P. And the third thing is, if you can actually define a composition where you conjugate by G and then you conjugate, or you conjugate by A and then you conjugate by B, then it's actually got to look like a homomorphism. So if you can define this composition, then it's got to have this properties of being a homomorphism. And then he proved something else. He proved that if you have a weak S homomorphism, then its image given by that by this map psi at the bottom here So here's psi. This image is in fact an endotrivial module. It's a Sylow-trivial endotrivial. Amazing. Okay, really, really good. It's actually not that hard to prove, but it was quite quite revealing. The trouble with the S homomorphisms is that they're not that easy to compute in general. But what Balmer showed was the following. He showed that if you take this set of all weak S homomorphisms, then this is an isomorphic to the kernel of the restriction. You can compose these homomorphisms. So it's isomorphic to the kernel of the restriction. And that's what we're looking for. Okay, so what does that say? It says that what you've got, if you're looking to classify all these Sylow-trivial endotrivial modules, what you have to do is you have to look for these weak as homomorphisms, and you've got to figure out when they're non-trivial or something like that. Well, here's what happened. The idea is to put it on the computer. I don't know if you all can see this. If you've got a Sylow subgroup for G, F, then we can define a function, a set of functions actually. As I say, Paul sort of encouraged me to put this on the computer because he knew I did this with Magma, and so I did it. Or I sort of did this conjecturally. I did it. The idea was it certainly I realized at some point that okay, you can figure out at least when this is trivial. That is to say, we define these functions. And the point is, okay, so row upper one of a P group. So these are functions from non-trivial P subgroups of S to subgroups of G. And what you do is you take the commutator subgroup of the normalizer of Q, and you multiply it times Q. So this is a subgroup of G. All right. So I'm going to do this for every non-trivial P subgroup. And then we can do, so that's row one. So how do you do row two? So to do row two, or inductively, what you do is, okay, you first compute row one, and then you take it, you add in, you sort of throw in, to get the next one, you throw in anything that you can get by just taking the normalizer of Q and adding in anything that exists, that is part of the already computed row function for any other P subgroup. You just throw those in. And what you realize from this pretty quickly is that any row I of S has to be in the kernel of any weak S homomorphism. That's what the formula was. You just figure out that this has to be in the kernel of any weak homomorphism. And so you get a theorem. And that is if for some row I of Q is the normalizer in G of Q, then for all non-trivial P subgroups, and actually you only have to get this for the Sylow subgroup, then what you get is that this thing, this T sub K, this group of Sylow-trivial endotrivial modules is in fact trivial itself, has only the trivial module as the only element. Okay, so in other words, these things all have to be these row I's of Q, these have to be in the kernel of any weak S homomorphism. Okay. So this led to a conjecture, and that is that in general, this group of Sylow-trivial endotrivial modules is the normalizer in G of F, modulo anything that you can get from this, by by running these row things. The rows are going, the row i's are going to converge after a short period of time because we are, after all, in a finite group, so won't go on for long. So that's the conjecture. And the way we get the conjecture was, okay, we had the theorem, and then whenever, if you go back to the theorem here, whenever this wasn't the case, whenever rho I of Q or rho I of S is not the thing, then you look for an endotrivial module, and we could always find it. So it just seemed to be right. So it came out to be a conjecture, and then Jacques Thévenin and I were actually able to prove it in a special case. It holds if S is abelian, if the Sylow subgroup is S. And this was proved using Burnside's fusion theorem. We thought about trying to do this more generally, but that would have required Alfred's fusion theorem, which is sort of a much more complicated, a beautiful theorem, but much more complicated. And so, but I told this to Jesper Grodal, who's a homotopy theorist, who had worked on fusion problems, a lot of fusion problems, and he, well, couple of years later, was actually able to prove this. And he proved it using homotopy theory methods. And here's what he actually showed. What he actually showed is that this TKS, this group of endotrivial modules, is isomorphic to the H1, the first homology group of the orbit category of the group G. And the orbit category is the category with objects G mod Q for Q non-trivial P subgroup, and whatever morphisms you can get by conjugation and inclusions. Okay. So Jesper was able to finally prove this. So, but this is the method. Okay, so what we wanted to do was, okay, well, we'll use this and try to figure this out for groups of Lie type. So we're going to work on finite groups of Lie type. First thing you have to do is say, well, what is a finite group of Lie type? Here's the definition that we are using. It's a finite group of Lie type if you take a connected reductive algebraic group over an algebraically closed field characteristic P, F a Steinberg automorphism. That is an endomorphism, an endomorphism of G, which basically becomes Frobenius after a few steps, after a few compositions. And you look at the G fixed points. You look at the fixed points under that Steinberg endomorphism. Okay, so that's what a group of Lie type is. We are using connected reductive algebraic group. If you look at the book of Muller and Testament, Gunther Muller and Donna Testament, they say semi-simple. And so this, by their definition, GLN of a finite field is not a group of Lie type. But we are being a little bit more general than that. Okay. So as I say, this is what a group of Lie type is. So what are your tools here? If you're going to do this, what do you have to do? Well, somehow you have to connect all this algebraic group stuff with what the structure is of the finite group and set that up right. But so from now on, as far as this lecture is concerned, we're going to set G to be an algebraic group defined over a field of characteristic P. We're going to let K be a field of prime order characteristic L. And so we're looking for endotrivial modules in characteristic L. And P is the defining characteristic. So this is the usual sort of notation that is used by people doing modular representations of algebraic groups of this type of stuff. So our endotrivial modules at our field K is going to be characteristic L. All right. Okay. Now, so how do we set this up? This gets a little bit technical, but let me run through it and I'll try to give you an idea of how it works. We're going to get this algebraic group G. It has a maximal torus. This determines a root datum D. You let X be the maps from G from the torus into the multiplicative algebraic group, and Y be the maps from the multiplicative group into T. And you've got associated roots to the action of T that are in X, and you've got co-roots defined in Y. So I take this R and R check, which are the roots and the co-roots. These are the X's. R is in elements of X, and R check is in elements of Y. If you've got a Steinberg endomorphism, this induces a map on the root datum, and so this is sort of our basic setup. We're going to work from root data in this way, and you can define all sorts of stuff because this works both ways. The other direction is if you start with the root datum and the action of the Steinberg endomorphism, then it determines the algebraic group and the endomorphism of that group up to, you know. So anyway, we can basically move from the algebraic groups into this sort of realm of root data. You can define a Weil group. That is, it's a finite group generated by the reflections in the root. You can define a fundamental group of the root datum, which is Y the co-root lattice of the co-root space Y mod Y tilde, which is basically the sublattice generated by the co-roots themselves. This thing has an ordered polynomial, generic ordered polynomial, and it turns out if your endomorphism is basically a Frobenius, then this actually gives you the order of the finite group. So if the finite group is defined over a field with Q elements, then this gives you an order. And then I'm not going to get into how you get this, but you know, well, as I say, these things have a generic group, generic order in some sense. If you take an outer automorphism, Steinberg endomorphism, action on the lattice that of tau and M is the order, then the point is if you take F of N and restrict it to the space X, the character lattice of the torus, then Q is going to be a power of P. Okay. So now how do we? So we want to get more specific. We pick out a field L. We sort of look at the. We're going to look at the order of Q mod L, basically, and this is going to give us a D, and D is going to divide one of these cyclotomic polynomials. These are cyclotomic polynomials, and so what we do is we define Y sub D to be the kernel of this, where you sort of go through the Weil group, and you take the largest possible rank. Okay, and this is what we call a maximal phi D sublattice, and we know that YD is independent of the choice of tau sub D up to W conjugation. So this is a sort of the setup that we use. It goes on and on. This is just a repeat of the last paragraph. We choose this YD. You define the phi D Weil group as the normalizer of the YD modulo of the central S. That is, by the normalizer, I mean the the set of elements of the Weyl group that stabilizes this sublattice YD, and the centralized stabilize it set-wise, and the centralizer stabilize it element-wise. And the phi d reg is the multiplicity of this in the order polynomial. Okay, the number of times that phi d occurs in the order polynomial. So this is it. Okay, now, so how do we get from algebraic group with a Steinberg endomorphism down to finite group? Okay, so well, what we're going to use is the theorem of Guatemala. This is sort of crucial to what we need. It says, suppose we've got a finite group G of Lie type. It corresponds to the simple algebraic group G. We let L be a prime different from Q, and let TD be a maximal phi d torus. With D right here, okay, so D here has to be the multiplicative order of Q mod L. Or in fact, it has to divide the order polynomial, it has to divide phi d evaluated at Q. Okay, if L is 2, then you take the order mod 4 relative to the order mod L. Okay. If G does not contain a non-central L subgroup, that is, L does not divide G of Q. Okay, okay, so here's the theorem. Theorem says, suppose that G does not contain a non-trivial central L subgroup. That is to say that L does not divide the order of the center of G. Then one of two things happens. Either L is 3 and G is type G2. Or there exists a Sylow L subgroup of G such that the normalizer in G of S is contained in the normalizer in G of the torus. Here S is the Sylow L subgroup. Okay. So this is how we get someplace. The point of this is the following. If G, there's a well-known theorem that we proved that occurs in several papers. If G has a non-trivial normal L subgroup, then every indecomposable Sylow trivial endotrivial module has dimension 1. So in that case, that is in the case that G contains a non-trivial normal or central L subgroup, then there's nothing to prove. We're already done. Okay, so we have to worry about the case where it does not contain such a thing. So other than this outlier, G2, then we've got this case that the normalizer in G of S is contained in the normalizer of G in the torus. And this can connect sort of our information about the Sylow subgroup with information about the torus itself. We're getting back to the algebraic group. And this is sort of how we put it together. In other words, it's sort of paraphrasing this, for the purposes of this proof, ignoring the G2 case, we need only find this row infinity of the G intersected with the torus. Okay, this is what we need to do. By the way, you know, if you actually read Guatemala's paper, this is not the way he states the theorem. His theorem says, okay, let's find all cases where the Sylow L subgroup where n sub G of S is not contained in the normalizer of the torus. And he makes a list. And it turns out that every one on the list except the G2 has this property of containing a non-trivial central L subgroup. So this is the case. So this is how we do the connection. Here's another thing we know. And this is sort of standard stuff. Is if you take the normalizer of the torus, of phi d torus, modulo its centralizer, this is the normalizer in W of Y sub d, this sublattice. modulo the centralizer, well, conjugated by the switch points on the tau d. This is our subspace WD. So what this says is, if you're going to do this, if you're going to go back and find this thing, then what you really need to do is, okay, first of all, you want to prove that the centralizer of T doesn't contribute anything. And then once you show that, then you can go over here and you can say, okay, what we really need to do is a look at the action of this group WD. The nice thing about this is a complex reflection group. We know what these things look like. These things are well documented. Lots of information on these. And so that's what we can do. We're also using the fact that the theorem of Steinberg tells us that if you've got a T-stable subtorus, then the contribution of this H1 of the centralizer, which as I say is actually, this is pi1 of the centralizer of the Y prime. This is going to be basically the YD mod. It's going to be YF mod, ZF. This is sort of what you get by factoring out the co-roots that vanish on the Y. Okay, so you can actually say what this centralizer is. But as I say, this is what we sort of need to get rid of, first of all. And so actually, so it gets you to this. So this is one of our theorems. Is that if you've got a finite group of Lie type corresponding to a root datum like that, then you let L be a prime not equal to, et cetera, et cetera. Then what you get is you get that this H1 of the orbit category, which is, as I have said, is this H1 of the orbit category. Which is the group of Sylow trivial endotrivial modules, or at least the P prime order of that is what you get as the largest quotient of G by with order not divisible by L, P, and L. So it's going to be the subgroup of H1 of G itself, modulo the stuff generated the elements of order L or P and P. So that sort of takes care of our case when you're looking at the L prime part of this group of the P prime part of this group of endotrivial modules. And so what we're really down to is looking at the P part of this group of endotrivial modules. And then you can do some other things. Again, you take a finite group of Lie type. You've got this WD. You take a sublattice complemented positive. You take M sigma, the finite group of Lie type corresponding to the centralizer of that thing. Then what you get is the P part of this, which is now what we're looking for of this thing, is that this is a zero map. In other words, you really don't, in such circumstances, you really don't have any contribution from the P part into this. Okay. And again, we're using this fact that we're going to use this fact. Yeah, we're using this fact that we can really do this on the level of the normalizer of this ID torus. Okay. And so the point of this is to show if what we really want to do is show that this rho 2, which is what we're looking for, is just the normalizer of this G. Actually, that's not the same thing. What I want is H1 of that normalizer. That's a misprint. Okay. So, and so finally what we get is we let G be a finite group of Lie type corresponding to a twisted group, with twisted root atom. And assume that the rank, phi D rank is at least 2. And then if Q is not 2 or 3, you assume further that the rank of D is 5, and D is not of type E7. And then you can basically compute what the H1 of the orbit category is. And the H1 of the orbit category is again the group of endotrivial modules. Okay, and again the case by case. We look at generators for the WD. We have an extensive appendix, which we're still working out the bugs in. Showing the given hypothesis, the generators all contain the commutator subgroups of the finite group of Lie type corresponding to some centralized in that way. And that basically is what we want to do. We want to show that all these generators, in fact, are in the kernel of any basic weak S homomorphism is what it comes down to. Okay. We do get some exceptions, so this is not the case. We get this out of Titt's list. Jacques Titt's years ago made a list of groups, finite groups of Lie type or G symbol where the H1, the P is not equal to 0, and it includes things like this. So these are the things that you want to avoid if you want the group of endotrivial modules to be trivial. So that's what he got, and using this, then we can go down this list and we can compute most of the exceptions. And what you get is things like small Lie rank, P equals 2 or 3. So you get A3 of 2 and B4 of 2. And in those cases, we can actually construct the exotic endotrivial modules on the computer. Case of F4 of 2, E7 of 2, and E7 of 3. And when L is 5, you actually get some other exotic cases. These are unfortunately too big. We haven't been able to construct these directly, but at any rate, this is sort of we can actually get some exceptions as well. So anyway, thanks for listening.
Any questions for Jon? I guess we'll bring you the microphone.
So this was a very long time ago. Obviously, we were working. So do you remember there was a where we had torsion-free generators, so we didn't know they were actually generators of the whole C. Maybe they were like 2 in the integers or something. Does this work with Grodal and your stuff actually let you know now when you have a generator?
Torsion-free generator.
Like we had modules, and we knew the torsion-free rank. We had modules that were free, but we didn't know if they were actually the generator.
You know, I don't know that we've actually gotten back to that and actually done that computation, but we should be able to figure it out these days. I think basically what we know now is that you should be able to run it on the computer and right out.
Other questions?
No.
So Jon, each one of this orbit category describes the endotrivial modules. Is the representation theory information in like H2 and the rest of the homology?
What is?
Like I was looking at you said H1 of this orbit category.
Yeah.
Is telling you about the endotrivial modules.
Yeah.
But then what about like H2 and the other homologies?
Don't know a thing.
All right.
Sorry.
You're prompted for someone. Other questions?
You gotta go under.
I was just wondering, this relativity is eventually stabilized?
Yeah. It's a finite group, but you've got an ascending chain of subgroups of the normalizing. So it can't go on for very long.
Do you have a sense of when that stabilizes?
There's some information on that in most of the actual cases that we compute, it's very fast. Maybe you get to row 3, but not very often. But I think you can actually pick examples where it goes further. But I guess where I think has some stuff in this paper where he actually figures this out.
So I'm guessing a lot of this machinery is coming from Jesper's endotrivial logic. Copy theory paper. Are there any other just interesting questions that are providing that you might think of?
I think there's a lot that hasn't been discovered yet. I mean, it's all involved with these fusion categories and things like that. And there's still a whole bunch of questions. Even just questions like how do you classify all the fusion categories and things like that. But I mean, this is, it all, in some sense, involves that in one way or another. I don't know if that answers your question or not. But.
So you started with the CGP founder at the beginning. So if you look at the CGP founder as an automorphism of the group of endotrivial modules, how do you describe this automorphism in the concept?
I'm sorry, I'm not yet.
So you started with the CGP founder. If you consider it as an automorphism of the group of endotrivial modules, which automorphism is this in the classification? What are the eigenvalues on the torsion Picard?
I don't think it's an automorphism. No. That's right. Right. I mean, it will take K to omega of K, and K is the identity element, but omega of K definitely is not. So it's not an automorphism. Well, the problem is, so on.
Are there similar results for the small quantum group attributes of unity, and you restrict it to the positive part?
Yeah. I don't know what happens in that.
But the question makes sense.
Yeah, I think it does.
So we take the small quantum group attributes of unity,
Yeah,
and you, instead of the Sylow group, you restrict it to the positive part of it.
yeah. We may be able to do something with this. What you're doing is you're computing the Picard group of the stable category, basically, is what this is about. And what happens with say, groups that doesn't happen with restricted Lie algebras is that you have this sort of Sylow subgroup where you can sort of get down to that, and that just plays this huge role. If you're doing this with restricted Lie algebras, there are a whole bunch of questions here as to what you get, or even worse with, say, Frobenius kernels of one sort or another.
But one natural choice will be to restrict it to the positive part.
Yeah, I think that's probably right. Yeah.
Any other questions for Jon? Same time,